In this video, we will go through the basics of electromagnetic radiation and focus on light calculations. So electromagnetic radiation is just a fancy name for light. Okay, and there's a lot of arguments about what light is, whether light is a wave or a particle, and we're just going to treat light as a wave mainly in this class. But if you go on and continue in more chemistry and physics classes, you'll learn that waves have both properties of waves and particles. And so light can reflect and be refracted. White light is made up of an electric field and a magnetic field, and the distance between two peaks in the wave is called the wavelength. So we see here the distance between two identical points. I typically choose the peaks, and that symbol is called lambda, which kind of looks like an upside down Y. Now, there's different types of light in terms of their energy. All light travels at the same speed, which is 3 times 10 to the 8th meters per second. Light does technically slow down when it travels through a fluid like air or water. So that speed, 3 times 10 to the 8th meters per second, it's a little bit rounded, but it's specifically for a vacuum. But we don't need to change anything because light travels almost just as fast through air. So there's radio waves. Those are the weakest. There's microwaves, there's infrared, there's visible, there's ultraviolet, there's X-ray, and there's gamma ray. And within the visible, red goes on this side, violet goes on this side, and it goes in the order of Roy G. Biv, okay? And gamma rays have lots of energy, and I'm going to change that to actually high energy. And then radio waves have very low energy. And it makes sense that gamma rays have high energy because if you look at how close together the waves are. And so things that get hit by gamma rays, I mean, they're just being bombarded because so many waves in such a small period of time. Where radio waves are really large, but there's a lot of distance between the waves, and so it's way less energy. Okay, they're much less frequent. So radio waves have low energy and they have low frequency. They have low frequency because there's a lot of distance between the waves. Gamma rays have high frequency. They're very frequent because the waves are so close to each other. Okay. So if you're in AP Chemistry, for whatever reason, the AP Chemistry College Board wants you to know that ultraviolet light, very high energy, that has enough energy that it could move electrons to different energy levels. So let's say we have our nucleus and we have an electron in the first energy level. If we zap it with enough energy, it could maybe move up to the fourth energy level, and then eventually it will come back down. Infrared light is less energy than ultraviolet, and so it doesn't have enough energy to move electrons, but what it does is it has energy to vibrate molecules. The microwaves are even less energy, but they're still kind of close to infrared, and so that can just rotate molecules. So just a little bit less energy means a little bit less movement. Okay? Now, if we go to our speed of waves, we've already talked about that the speed of light is 3 times 10 to the 8th meters per second in vacuum. And on your formula sheet, you have this formula, which what it says is that the speed of light is a constant. And we know that the distance between waves is called the wavelength. And that's lambda. And then this, it looks like a V, but it's really the Greek letter nu. And this is frequency. Okay. Frequency is measured in hertz, seconds to the minus 1 power, which is 1 over seconds. So it could be any of those. And we'll just see how this works. Here, the question says, what is the frequency of light that has a wavelength of 550 nanometers? Okay, so we want to solve for frequency, and we're given lambda. Well, our equation is C equals lambda nu. C is 3 times 10 to the 8th meters divided by seconds. We want to solve for the frequency, and so what we need to plug in here is a wavelength. And a lot of people would plug in 550, but that's not what we need to do. Is we need to say, oh, if I need meters per second, and I must need to have something with meters, and nanometers just doesn't quite cut it for us. So we'll say 550 nanometers. In 1 nanometer, there's 10 to the minus 9 meters. And so what I get is I get 5.5 times 10 to the minus 7 meters. I can plug that in here. I'll divide that over. And my frequency, let's see what that'll be. Is going to be 5.45 times 10 to the 14th. And let's look at our units that cancel. Meters and meters cancel, so we're left with per second. So you can write it like this, per second. You can do seconds minus 1, that's the same thing. Or what's common is that we'll say hertz. And if you look at like your car radio, the stations, like 99.5, that was typically represented in megahertz, okay? And so if we have high frequency, which we do here, the waves must be really frequent, so they look something like this, where they're really close together, which means the distance between the waves would be very small, and we see that this is small. Okay, the last thing we're going to do here is the amount of energy that a wave has, or that light has, is directly related to the frequency, because we've talked about when waves are like this, where they're close together, this is high energy. Okay, they're very frequent. Where if waves are like this, the waves are further apart from each other, and so they're low frequency. Okay, we know high energy and high frequency, that's a direct relationship. And so there's an equation, and what it is that the energy of a photon, which is a particle of light, is directly related to a constant. This is called Planck's constant. And that is 6.626 times 10 to minus 34 joules times seconds. And V is not V, but it's really nu, and that is frequency. And that needs to be in hertz. Okay, so our first example here says, what is the energy of red light if it has a frequency of 4.567 times 10 to the 14th hertz? So the energy of one photon is equal to Planck's constant times its frequency. We know Planck's constant is 6.626 times 10 to the minus 34 joules times seconds. We'll multiply it by the hertz, which is 4.567 times 10 to the 14th per second, equals the energy of our photon. We'll plug that into my calculator here really quickly. It looks like we should get something times 10 to the negative 21st maybe. I was off by just a little bit. We get 3.03 times 10 to the mega 19. And if we look at our units, and I specifically did not write hertz here so that you could see the units canceling a little bit better. Hertz is the same thing as per second, so seconds in the denominator, seconds in the numerator, those cancel and we're left with joules. But this is specifically the joules for one photon.